Swayam Prabha. Digital India. Educated India.
So passivity by output selection is a possibility, okay, as long as your system is stable in the sense of Lyapunov. Okay, so great. So there is at least some hope. Now, like I said, what happens when you don't have a stable in the sense of Lyapunov system? Okay, then you go for what is called feedback passivation. Okay, you try to use the feedback to get passivity. That's the idea. Okay. So what is the deal? We are now not making any assumptions on this guy. Yeah. What we are saying is you have this input output system. We are already specifying the output also in this case. All right. The output of course might come from here, the previous method itself, but now we are no longer saying that there is some kind of there is any stability in the sense of Lyapunov for this system, yeah, because which is what we assume for the first case. But we assume there exists some feedback. Okay. So what are we going to do? We are going to sort of plug in a feedback in the system. Okay. Now the question is, what is this feedback doing? Of course we have to ask. Once we plug this in, and again this material is sort of taken from Khalil, right, but there it is, a lot of it is stated as theorems and proofs and all that. I am not doing that, I am doing it more in a step by step way, so that we figure out what is happening. Yeah. So as usual we assume all the Lipschitz smoothness and all the nice things. Then what am I doing? What I am doing is I am just proposing some feedback. If you notice, this is a pretty general structure for a feedback. It is not, there is nothing very specific or special about it. What did I do? I broke the feedback into one term and then another term which contains some additional thing that I can play with, I can sort of prescribe later on. Okay. So I have taken this control and I have reduced it to this control. Okay. So but as far as we are concerned, these are pretty much equivalent, as general as it gets. It is some function of x, another function of x multiplied by new control, as simple. Now what is the advantage? Of course we are as usual assuming some more Lipschitz and smoothness and all that. For just to keep things simple, let us assume everything is smooth anyway. Yeah. If you substitute this control back here, you are going to get this sort of an expression. Okay. And I have done nothing but substitute the control here. Now if it so happens that this system is passive in Vy, then the system is said to be feedback passive. Okay. But again looks very general and looks like it is not going to help us at all, but it is, because we are just trying to generalize this situation. We are going to use this control somehow to sort of give a feedback term, right. This will sort of plug in a feedback term, and this feedback term is potentially going to make this Lipschitz make this stable, and then you can sort of choose this y and so on. Okay. So this is one step beyond what we have here. Okay. That is the idea here, that is the idea. Yeah. And this is called feedback passivation, is more like a definition, if you may. Yeah. That after plugging in some feedback which is very very general, if the system turns out to be passive with this y and with this sort of drift system, then and with this new control v, not the old control u but the new control v, then the system is feedback passive. Okay. And to illustrate this, we actually look at now one rather serious and useful example. Yeah. This is the control of robot dynamics in joint space. Yeah. You are already you can very quickly get into the controlling a robot. Okay. And this is like a manipulator. Any robotic manipulator will have this sort of a dynamical system. Okay. We will spend a couple of minutes trying to understand what the terms are. Yeah. Anyway, some of you might have seen this sort of model is typically arrived at by using Lagrangian Yeah, those of you who have done any kind of robot modeling will know. So this set of model is arrived at using the Lagrangian method, yeah, or Hamiltonian, but typically Lagrangian. Yeah, Q is what is called the generalized coordinates. So if you have a robot, let me see, if you have a robot which is like has a revolute joint like this, right, and then here there is no revolute joint, but how do I say? Okay. If you look at this picture, what do you see? There are three sort of degrees of freedom, if you may, yeah, or three sort of in the sense coordinates, not degree, let us call them coordinates. What is this? In order to specify this robot, I will need to specify this angle alpha 1, okay, then this angle alpha 2, right. So, it is like shoulder this, yeah, shoulder and this, right, alpha 1 and alpha 2, but here which I can't do the third thing, yeah, I am saying that my wrist can sort of move in and out. It is a linear joint, linear actuator, okay, linear actuator on one of the arms, yeah, you can see that this is possible. I mean, I can make it out with this guy. So, this is a robot, yeah, so this is one angle, this is the other angle, and this thing can move also, yeah. You can imagine I can make a robot like this, I mean for many reasons, yeah, just for fun if nothing else, yeah. All right. Now, what is funny or odd about this is that all coordinates are not angles or all or x y's. So, they are not in the same type of coordinates, if you may, yeah, they are either angles or positions and so on and so forth, yeah. But when you do Lagrangian modeling, you can actually look at them all together and you call them generalized coordinates, yeah. They can be positions, they can be angles, they are all combined in one vector, and this is called generalized coordinates, okay. That is the reason for naming them generalized coordinates, because they can be positions, angles and so on and so forth, no problem, okay. Again, in the mechanical system context, again in electrical system it can be voltages, currents and different things, yeah, completely different things, different units, yeah, they are combined in one, yeah. So, and q dot is of course generalized velocities, right. So, in this case it alpha 1 dot angular velocity and x dot which is linear velocity, yeah. So, and then you have the system matrices, which is the first and the most important one is the M of q, which is the inertia matrix. It is called the inertia matrix, and not difficult to sort of compute. It sort of actually captures the inertia of the robotic system. If it moves around this origin, then what is the mass distribution? Typically, this will be a function of the coordinates itself, yeah. In very unusual circumstances will it be independent of the coordinates themselves, yeah. Mostly it will be a function of the coordinates, but it will be symmetric positive definite. Inertia is always symmetric positive definite matrices, okay. Then you have the C, Q, Q dot, which are the centrifugal and Coriolis forces, okay. Again, because it is robot and mechanical system, so you know exactly what these are, yeah. And then there is D, which is the viscous damping. This is like if you have these joints and then there is damping on the joints, yeah, or there is damping in the linear actuator, right, then here, then there is some viscous damping, and that depends, that sort of always scales the velocity. And then finally you have the G, which is the gravity term, okay. So, this is standard notation. I do not think even books will change more. If you go from one text to the other, I do not think they will even change the symbol of the or the letters also. Thankfully, this is one of the more standard notation. M will always signify the inertia, C will always be the Coriolis and the centrifugal and or centripetal, whatever. Then you have the D and the G, which is the damping and the gravity. And then you have the control finally, yeah. Control of course can be, you can actually maybe have a motor here, and you can have some linear actuator here, pneumatic actuator or whatever. Okay. So this is the control. Okay. So this is the system that we are looking at. Yeah. And one of the things that's known for, because we have arrived at this via Lagrangian modeling, is that m dot minus twice c is a skew symmetric matrix. Okay. This is known for this robotic type system, it will always hold. Yeah, this is nothing very unusual, system property. And what does it mean for if a matrix is skew symmetric, then the corresponding quadratic form is always 0. Okay. This is again a property of skew symmetric matrices. Okay. So again, whenever we deal with practical real systems, then we have to identify these properties of the system. So typically somebody who has been working on these systems for a while, they will know these. Yeah. So whoever designs controllers for these systems, they will always know this, there is no two ways about it. Yeah. So m dot minus 2c skew symmetric, therefore any quadratic form using m dot minus 2c turns out to be 0. Yeah. Okay. What is the objective? Tracking. We have until now not done any tracking problem. Okay. So this is the first tracking problem. Okay. What is the objective? Track a reference q of r. Again, this reference, and we are doing everything in the joint space, by the way. Yeah. In reality, you might be applied guys might be interested in the position of this guy, the world position. Yeah. What is called the end effector position. Yeah. Not this x, not this x, but the world x y z. Okay. You might be interested in applications on that. Okay. But you can always reduce it to some trajectory in alpha 1, alpha 2 and x, yeah, by using the inverse kinematics. Yeah, for any robot this is possible. Again, we are not going into that much detail, but the idea is any world space problem can be converted to a joint space problem. Yeah. And so we are doing the control in the joint space only, not in the world space. Yeah. Now if I want to track a constant reference, then I construct an error like this. Okay. And what happens? We write the dynamics of the error. It comes out to be this guy. Okay. Do you believe me that it comes out to be this guy? Yes. What is it? Go ahead. There is a G term there. Yeah, what are you saying?
We are taking the difference between the reference and the actual, then I don't think there should be a G term.
Okay. I made this a simplified problem. Okay, I will. I have basically chosen a constant reference. So QR is actually a constant. So I am actually doing an easy problem here. Yeah. Actual trajectory tracking would be, it's a time varying trajectory. In that case, the trajectory also will have to satisfy an equation like this typically. Anyway, we will go there later on, not right now. Yeah, not right now. Right now we are doing an easier problem. The reference is a constant. My angles are at some constant value. My linear position is at a constant value. I want them to go to another constant value. That's it. Okay. Now if you look at this again, q minus qr, qr is a constant. So any derivative, so left hand side contains only derivatives, right. So any derivative, E double dot is actually Q double dot, E dot is Q dot, and GQ is just GQ, nothing changes. Okay. Just because I chose a constant reference, yeah, just to make my discussion in class simple. Yeah, otherwise it will take a long time to reduce the problem itself. Okay. So what we want is E equal to 0 to be globally asymptotically stable. Okay. So you see that the dynamics of E and the dynamics of Q are the same just because we have a constant reference, nothing magical. I didn't do anything. Yeah, you are right. If there is an actual reference, then we'll have to do the gravity will cancel. Okay, we have to do all those funny things. But we are not going there. Now, what are we claiming? We are claiming that this kind of a control will give us feedback passivation. What is feedback passivation? It means that after I plug in the control and with some output, I will get passivity. So my claim is that this control gives me feedback passivation. It's obvious that the first term is just to cancel this guy. So let's not even worry about it. It's just going to, if I plug in U, it's just going to cancel this guy. Yeah. Then there is a nice negative term in the error. We love these terms, right? Always. It's a proportional control, yeah, if you may. And then I have some new control that I will figure out later on. Yeah. But my aim is to get passivity in this case. Okay, I just want to get passivity. Let's plug in and see what happens. Yeah, if I plug in, this is what I get. Gravity cancels out and the KPE went from here to here. So I just have this system. Okay, now I consider this storage function V as this guy. Okay, this is a very standard construction. Yeah, it is just taking notice, by the way, I have not written this in state space form. All of you should always be watching these things. I didn't write this in state space form. I am directly working with the second order dynamics. Technically it will be nicer if you wrote this in state space form and so on, but because it is pre-multiplied by an m, it's a little bit painful, but you can always do that. You can just write this as E1 dot is E2 and m q E2 dot is whatever. Okay, this would be the state space form, yeah, where E1 is equal to E and E2 is equal to E dot. Okay, if I choose that, then I would get a state space form. Let's not worry though, yeah, pretty easy. All right, great. Now I am saying that this is a very standard construction for a Lyapunov candidate for the robotic system. Very standard construction. If you get a robotic system, try this Lyapunov function, Lyapunov candidate. Okay, great. Why is this a nice candidate? First of all, M is symmetric positive definite. Okay, for all Q. Therefore, this is already a nice positive term. Kp was chosen to be positive definite. Obviously, I mean, I don't know if I wrote this here. Really hope. Oh, disappointing. Kp in the general case, yeah, this is positive definite matrix, symmetric matrix. Okay, therefore this is also a positive choice, nice choice. So this is actually a quadratic, right? Just a quadratic form, yeah, and both are positive definite matrices. So it's almost like x1 squared plus x2 square, yeah, or k1 x1 squared plus k2 x2 square, where k1 and k2 are both positive numbers. It's just the matrix vector extension of that. Okay, standard Lyapunov function, yeah, and this is, you should get used to this sort of a construction. If I take the derivatives now of this guy, what happens? This is just E dot mq E double dot. Yeah, I am using the product rule. So E dot transpose times mq times E double dot, because it's a vector, I am just being careful of the transpose and all that. I am not allowed to change orders of things and all that mess. Otherwise, it's the same. And the second term is E dot transpose half E dot transpose m dot q E dot, and because there is derivative of this also. Okay, you could have done this twice, half E double dot transpose m q E dot and half E dot transpose m q E double dot, but it turns out to be the same things, right, because of scalar, transpose of scalar is scalar, yeah, which I made you write. Yeah, this is a scalar quantity, so I can keep taking transposers. So this is also a scalar quantity. Okay, and then again derivative of this is E transpose kp E dot, yeah, because this is scalar, I can keep flipping, no problem, same thing comes out. Okay, great. This I want to be less than equal to V transpose Y. all right. This I want to be less than a V transpose Y, okay. I need you to do this. As you can see, it's the exercise. Now you see, I have to plug for E double dot here, right, which is this. Actually, sorry, I have to plug for NQ E double dot here, which is this guy. Yeah, brings in the V, brings in the control, new control V, and then there is E transpose KP E dot, yeah, which is actually very nice. You will see that it's a nice term. So basically this term contains the new control V, and now what I want you to do as an exercise is choose a output, anything as output Y, such that this quantity is less than equal to V transpose Y, where V is this new control, and then basically you would have achieved feedback passivation. Not just that, I also want you to, after you find the output Y, I also want you to show zero state observability of this system for this V-Y pair, okay. So this is a very, very nice and obviously a relevant example. We already moved into something real, yeah, and you will also be doing simulations on this, okay, with some real numbers that I will give you, yeah. So please look at this carefully. You will have enough time, it will be the next homework. So you will have enough time, look at this carefully, understand it very well. If you have any doubts, you ask me, but make sure you understand it very well so that you are able to do this exercise, yeah. I mean, if you can crack this theory part, okay, because once you have this output Y and this new input V, you know that the control can be just minus phi Y, right, because of the theorem that we have already, yeah, it's all set. So all you have to do is this, show that this is less than equal to V transpose Y for some output, artificial output that you choose. It doesn't have to be, real, okay, but again check and see what comes out, yeah. You will see that something very nice comes out on the left hand side, yeah. The system, this the Lyapunov candidate and the system has very nice properties, yeah, which is why controlling robots is actually, I mean, designing control for robots is readily easy, yeah. So please sort of start on this exercise, just get yourself a warm start, try to understand what's going on with these terms and so on, yeah, and see how you can use these properties, yeah, to complete this analysis. So once you can compute the left hand side properly, that's all you need to do. Once you compute this left hand side properly and carefully after substituting the E double dots, you will yourself have some structure like this, and then you just have to choose a Y, because otherwise it will be difficult, right. You should have a structure that looks like this here, okay, all right, okay, cool, thank you.